Hello, and welcome to this training event. This is Nicole Zovac, a Technical Product Specialist with SKC. I am pleased to present this webinar on air sampling to meet the OSHA final rule on respirable crystalline silica. The training today is targeted to the technician level to help health and safety personnel in construction as well as general industry better understand how to collect an air sample for silica and how to compare the results to the OSHA permissible exposure limit. Before we get into the details of sampling, let's just take one slide to consider what's the big deal about silica. Why does OSHA say if it's silica, it's not just dust? You probably know that silica exposures have been linked to the lung disease silicosis. But you may not know that silica exposures can also lead to lung cancer, kidney disease, lupus, and rheumatoid arthritis. Today, you will learn how to take an important first step in protecting yourselves and others from the hazards of silica: air sampling. But if air sampling is brand new to you, it may seem overwhelming, but just relax. Air sampling is as easy as 1, 2, 3. 1 is the sampling pump. 2 is the pump FLOWMETER. And 3 is the collection device for silica dust. The webinar today will include introductory notes on the OSHA standard itself, technical details on each of the 3 components used to collect an air sample, important considerations for the sample duration, how to compare air sampling results to OSHA's silica exposure limit, and a field detection tool that can help you manage the site and serve as a supplement to compliance air sampling. Now let's look at some introductory notes on OSHA's new silica standard. First, let's look at the permissible exposure limit, or the PEL. The new OSHA limit essentially cut in half the amount of silica that workers can be exposed to over the 8-hour workday. Next, let's get introduced to a very important concept in air sampling: the time-weighted average, or TWA. Because exposure levels can vary throughout an 8-hour work shift, OSHA sets exposure limits as an average. With the TWA, all of the high and low silica levels are averaged with respect to time. We will cover this in more detail later. So what does this all mean to you and your company? Employers must ensure that no employee is exposed to more than 50 micrograms of silica per cubic meter of air as an 8-hour time-weighted average. An action level of 25 micrograms of silica per cubic meter of air was also set. Just like the name action level, if your levels are over 25 micrograms per cubic meter, you have to take some action to protect workers even though you aren't over the PEL. If you work in the construction industry, you should be familiar with what I call the famous Table 1. Given the variable nature of construction work, this table was included into the OSHA standard as a convenient option for compliance. The good news is that employers in construction can skip air sampling if they use specified dust control measures for designated tasks. The bad news is that there are only 18 tasks or control measures listed in the standard. And for job tasks that are not listed in Table 1, or if the controls are not fully implemented, employers are required to assess the exposures of employees who may be exposed to silica above the action level of 25 micrograms per cubic meter. Whether you are in the construction or in general industry, you can assess the exposures of employees by using the performance option or the scheduled monitoring option. So let's first talk about the performance option, which is quite unique for OSHA regulations. This option allows employers to assess workers' silica exposures using any combination of actual air monitoring data or so-called objective data. Objective data includes things like industry-wide surveys that document typical exposure levels. It also includes historical data that you may have on file for specific tasks. Keep in mind that objective data must closely reflect the work conditions at your site. And the burden is on the employer to demonstrate that any objective data being used complies with this requirement. A common question is, where can you find objective data? If you don't have any air sampling data in your own historical files, the best thing you can do is an internet search. Manufacturers of drilling and grinding equipment provide data for their tools. Trade associations also provide opportunities for members to post and share data. Here, you can see an example of objective data available online that is supplied by Makita for their rotary hammers with dust extractors for concrete drilling. This slide shows the requirements if you are using the scheduled monitoring option. Initial air monitoring must be done unless you can demonstrate that workers are not exposed above the action level. More monitoring may need to be done based on the results. If the results are above the PEL, you will need to, of course, control the exposures and repeat air sampling every 3 months. If the results are above the action level, you will need to repeat air sampling every 6 months. You can discontinue air sampling when 2 consecutive measurements, 7 days apart, are less than the action level. One of the big questions that health and safety professionals face when sampling any air contaminant is how many samples to take to adequately assess exposures. OSHA provides some guidance on this in the new Silica standard. OSHA says to collect 1 or more samples that reflect each shift, each job classification, and each work area. If several employees do the same task in the same shift in the same work area, you don't have to sample every single one. You can do representative sampling by sampling those with the potential for the highest exposures. For most of us, it's hard to imagine just how much silica dust is 50 micrograms per cubic meter of air. Shown on this slide is a good explanation shared by a health and safety professional. Imagine a pile of dust the size of a standard pencil eraser. This amount of dust in a box that is 3 feet by 3 feet by 3 feet would be over the current PEL of 50 micrograms per cubic meter. That's not a lot of dust. OSHA also has some new requirements for analysis. The laboratory must analyze for all 3 forms of silica, including quartz, cristobalite, and tridymite. The most common form of silica is quartz. Quartz may morph into cristobalite with high temperatures like in a foundry, but tridymite is normally only associated with volcanoes. So talk to your lab about ways that you can reduce the burden of analysis for all 3 forms by documenting the type of silica through the SDS, historical data, or the analysis of a bulk sample of your dust. Now that we covered the OSHA standard itself, let's move on to the 3 key components for silica sampling. 1 is the sampling pump, which simply pools air. 2 is the pump calibrator, also called a FLOWMETER. This device measures the flow rate of the pump with a high degree of accuracy. The third thing is the sample collection device. This separates and collects the small respirable dust particles from the dust cloud onto the filter for the lab analysis of silica. Let's now take a closer look at the first key component, the sampling pump. There are a number of sampling pumps on the market with various features and price ranges. So how do you know which one to choose? Here are some factors to consider. The flow rate. Can the pump sample at the flow rates required for the collection of respirable dust? This is typically 2 liters a minute or higher. Power. Can the pump continue to sample at a constant flow rate for 8 hours, even with a high dust load on the filter? This is very important. You can buy cheap pumps on the internet, but when there is any sort of dust buildup on the filter, the pumps die or the flow rate drops off, leading to an invalid sample. You must have a constant flow pump for any sort of dust sampling. The size and weight. Will the pump be acceptable for workers to wear the full shift? And automatic features. Is your budget limited to a basic pump? Or can you purchase a pump that offers the convenience of intuitive touchscreen operation like your cell phone, along with a timer and programming options? Here you can see a basic pump available from SKC called the AirCheck 52. With a flow rate up to 3 liters per minute, this pump can be partnered with most sample collection devices used for the respirable crystalline silica. The AirCheck 52 is a constant flow pump which will maintain the flow rate as the dust builds up on the filter. The AirCheck 52 has a very simple operation using the on-off switch, flow adjustment screw, and a timer to keep track of the sample time. This basic pump cannot be programmed for a designated sample time with an automatic shutdown. If you have a little bit more budget money, it will be very well spent on the AirCheck Touch. Like your cell phone, this pump is very intuitive. You can figure out how to use it without reading the instruction manual. The AirCheck Touch has a very powerful battery that can provide constant flows up to 5 liters per minute and long run times. You can also program the flow rate and the sample time directly from the touchscreen or by using the optional SKC software. Now we will move on to the second key component for air sampling, the pump calibrator, also referred to as the pump flow meter. I'm sure many of you use a lot of different types of meters in your job. A pump flow meter simply tells you how much air the pump is pulling. That's it. The term calibration can be a point of confusion for those new to air sampling. Calibration of pumps does not refer to an annual service done by the pump manufacturer. Pump calibration is done by you, the user, to set and verify the flow rate of the pump to that required in the sampling procedure. This must be done before and after every sample that you take. The average of the pre and post sample flow rates is used to calculate the total air volume. The air volume is simply how much air the pump pulled during the sampling period. Some new users may question why they have to calibrate the pump every time they collect a sample. Here's why. With every silica sample that you submit to the lab, you have to advise them of the total air volume that was pulled through the filter. The laboratory will measure the silica dust on the filter and will use the total air volume that you provide to calculate the concentrations of silica in air. Here's a little more information on this. The pump flow meter measures the flow rate of the pump in liters per minute. This flow rate is multiplied by the total sampling time in minutes to determine the air volume in liters. The air volume in liters is sent with your paperwork to the laboratory for each one of your filter samples. The lab uses analytical instrumentation to measure silica on the filter in micrograms. Then they use the air volume that you supplied in liters convert this to cubic meters, and report back to you an airborne concentration of silica in micrograms per cubic meter of air. Many pumps on the market have a display or some other sort of flow indicator on the pump itself. These are not adequate for flow calibration for compliance sampling. You must have a designated calibration device that is of high accuracy and certified to a national standard. Annually, the calibrator must be recertified by an ISO-certified calibration laboratory. Don't worry, it's only $195 to recertify at the SKC calibration lab. You may also want to have some less expensive field devices such as rotometers. You can calibrate these devices by yourself by comparing the flow indication on the rotometers to that of your high accuracy certified calibrators. Shown here is a certified calibrator with extremely easy one-button operation. The SKC Checkmate takes a reading once a second and displays a moving average of the flow rate. It can take readings up to 5 liters per minute, which covers the range for most silica sampling. SKC includes the Checkmate in our deluxe silica sampling kits, or it can be purchased or rented separately. The Checkmate is very popular due to the size, simplicity, and a price that is half of our competitor models. In addition to your certified calibrators, you may want to have some inexpensive rotometers that can be easily transported and used to calibrate pumps in the field. SKC includes rotometers in the basic silica kits. Rotometers are cheap and easy to use, but keep in mind that you have to check rotometers regularly against the high accuracy certified calibrator to ensure the flow indication is accurate. Regularly is not defined by OSHA anywhere, but once a month is typical. Also note that rotometers are affected by temperature and atmospheric pressure, so check it against your certified calibrator under conditions of use. Here are some tech tips on calibration. Best practice dictates that you let your pumps run about 5 minutes after removing them from the charger before you do calibration. This is just to ensure that the flow stabilizes after coming off the charger. Set and verify or calibrate the pump flow rates with the sample collection device attached to the pump. This sample collection device will be used for calibration only. Make sure to use a clean sampler to collect a sample in the field. After sampling, recalibrate the pump with the sample collection device in line. Some users post-calibrate with the actual sample from the field in line. SKC, however, feels that it is better to recalibrate with the calibration sampler to avoid contamination concerns, but you may wish to discuss this issue with your lab or supervisor. If you are new to air sampling, you may find it interesting that industrial hygienists seem to love 5%. You should ensure that the pump flow rate is within plus or minus 5% of the required flow rate. If you are using a piston or bubble meter, take at least 3 flow measurements that agree within 5% and use the average as your flow rate measurement. If your pre- and post-sample flow rates differ by more than 5%, your sample is called into question and should be repeated. Again, if you are new to air sampling, it's easy to get confused on the what goes where when calibrating your pumps with the sample collection media in line. So here's a helpful tip. Set up the pump and sample media like they're ready to be placed onto the worker. Then attach the inlet of the sample media to the calibrator to check the flow rate. Note also that sample collection devices used for respirable dust cannot be attached directly to the calibrator. A respirable dust CYCLONE, for example, has a slit on the side where the air comes in. You can't attach a piece of connecting tubing to a slit. So calibration adapters are available that allow you to easily connect the sample collection device to the pump calibrator to verify the flow rate. These are inexpensive devices, and you just need one or two to use with your calibrators. Some respirable dust cyclones, like the old Dor Oliver, do not have a calibration adapter, so it is standard practice to use a calibration jar. Honestly, you want to avoid this if at all possible. It is much easier to use a respirable dust sampler that has a calibration adapter. The third key component is a sample collection device for respirable crystalline silica. One of the biggest changes in the OSHA final rule on silica is the new performance criteria specified for samplers. Respirable dust samplers must meet ISO standard 7708. You may also hear the standard called the ISO CEN convention. This is a global standard. ISO is the International Standards Organization, and CEN is a Committee for European Normalization. This slide may be a little too techy, and it's just for information only, but I just wanted to illustrate for you the performance criteria in ISO 7708 that was incorporated into the OSHA standard. ISO 7708 is essentially a collection efficiency curve that specifies the efficiency of the sampler for particles of designated sizes. For example, if the particle is 2 micrometers in diameter, the sampler should be about 95% efficient. If the particle is larger, around 9 micrometers, the sampler only has to be around 5% efficient to still meet the criteria. There's a lot of data points on this curve, but in the health and safety profession, we normally only talk about one data point for consistency and simplicity. That data point is called the 50% cut point. This is the particle size that the sampler collects with 50% efficiency. If you look at the graph, go to 50% and drop down to the y-axis. You can see that particle size is 4 micrometers. Again, this is just some techie background information so you understand the performance criteria. Let's get back to the basics of sampling. Ultimately, silica dust is collected onto a filter for lab analysis. Preceding the filter, however, is a particle size selective device that will separate the smaller respirable dust particles from the larger non-respirable dust in the dust cloud. Why do you have to use a respirable dust sampler? Because OSHA says so. That is the way that silica is regulated. Respirable dust samplers separate the smaller respirable particles from the larger particles in the dust cloud and will collect the particles onto the filter for analysis when connected to a sampling pump. Collecting larger, non-respirable particles would inflate the results of the sample, overestimating exposure. Let's now look at the respirable dust samplers on the market that meet the OSHA final rule. Respirable dust cyclones are the traditional samplers used for respirable dust sampling. Cyclones are inserted into filter cassettes containing PVC filters and are attached to sample pumps. Air enters through a slit on the side of the cyclone, which creates cyclonic action. Through centrifugal force, large particles fall into the cap at the bottom, called a grit pot, and are discarded. Small particles are thrown onto the filter for analysis. Please remember to keep the cap or the grit pot on the cyclone during sampling. For some reason, many users want to remove the cap, and that is incorrect. After sampling, the cyclone is removed and the filter is capped and sent to the lab. Do not turn the cyclone upside down until you have removed the filter. If the large particles in the cap at the bottom get dumped onto your filter, your sample is invalid and the results will look very high. Finally, clean the cyclone with soap and water between every use, or the dust stuck to the interior walls of the cyclone will affect your results. If federal OSHA shows up at your door, they will be sampling using the very old nylon Dore-Oliver cyclone. They have been using these for years and don't plan to update to newer technology at this time. Note, however, that the new OSHA standard allows employers to use any respirable dust sampler that meets the OSHA 7708 criteria. Newer cyclone samplers include the SKC aluminum cyclone. This cyclone is listed in the OSHA final rule and is operated at 2.5 liters per minute to meet ISO 7708. The newer aluminum cyclone has several advantages over the old Dore-Oliver cyclone. Metal construction eliminates static electricity concerns. It has a larger collection area since the cyclone is inserted into the middle ring of a 3-piece filter cassette and is sampled open face. It also has a handy calibration adapter. Any device made out of aluminum is considered a spark hazard in the underground coal mines. So another cyclone that can be used in this work environment and in others is the SKC GS3 cyclone. It is conductive plastic, so there is no static electricity concerns, and it is not a spark hazard. This cyclone is designed for use at 2.75 liters per minute to meet the OSHA criteria. It is very important to note that each cyclone has a different operating specification to meet the required performance criteria. Be sure you know the flow rate specified for the cyclone that you are using. The flow rate for the Dore-Oliver is 1.7 liters per minute. The SKC aluminum is 2.5 liters per minute, and the GS3 is 2.75 liters per minute. If you use the wrong flow rate, the data collected is meaningless, and this is a very expensive mistake considering the cost of analysis and professionals' time in the field. Cyclones have been around for a long time, but in recent years, a new sampling option has emerged. The good news is that OSHA permits employers to use any sampling device that conforms to ISO 7708, also known as the ISO CEN convention. The OSHA standard goes on to say there are also personal impactors available for use at flow rates from 2 to 8 liters per minute that have been shown to conform closely with the ISO CEN convention. This data was supplied by SKC to the OSHA docket on the new PPI samplers. Here you can see a PPI sampler opened up into its two pieces. Instead of a cyclone that separates the large and small particles by centrifugal action, PPI impactors have 4 internal pre-oiled plates that scrub out larger particles. The impactor plates are sonically welded into place by SKC and require no assembly. The pump draws the air onto the PPI. Larger particles are scrubbed out onto the plates, and the smaller respirable dust is collected onto the PVC filter for analysis as usual. Same filter, same analysis as with cyclones. Here you can see the data that SKC sent to OSHA showing that the PPI samplers closely match the ISO 7708 standard specified in the OSHA final rule. The most popular model of the PPI sampler is the plastic disposable model shown here. The disposable PPI requires no assembly, is small and lightweight, and there is also a handy calibration adapter. The biggest advantage, however, is that you can invert the sampler without causing the large particles to land on the filter, invalidating the sample. If you invert a cyclone, you have to repeat the sampling another day. Single-use disposable PPI models are available for use at either 2, 4, or 8 liters per minute. The choice of flow rates allows you to choose the best sampler based on your sample times and expected concentrations. Most accredited IH labs are supplying these directly to clients, or they can be purchased from SKC. By far, the #1 most popular PPI model is the one designed for use at 2 liters per minute. If you want to sample a shorter duration, you can consider the option of using the 4 liter per minute PPI or the 8 liter per minute PPI. Keep in mind, you will need sampling pumps that can achieve these flow rates. Shown here is the AirCheck Touch pump on the top, which has flows to 5 liters per minute, and the Leland Legacy pump near the bottom with flows to 8 liters per minute. Let's now summarize your daily routine for air sampling. First, charge your pumps overnight. Upon arrival in the morning, remove the pumps from the charger and turn them on. Let the pumps run for at least 5 minutes while you go get some coffee. Calibrate each pump with sample media designated for calibration only in place. Document the pre-sample flow rates for each pump along with the pump serial number or ID. Replace the sample media with that to be used in the field for sample collection. Next, attach the pump to the worker's belt and the sample collection device in the worker's breathing zone or shirt collar. Turn on the pump to begin sampling. Note the time of day that the pump was turned on. Periodically observe work activities and take field notes documenting the worker's tasks, environmental conditions, work conditions, and unusual events. Full shift sampling is preferred regardless of the duration of the individual task, since OSHA has set the PEL as an 8-hour average. If the worker has to leave the job site, just pause the pump off and remove it from the worker. Upon return, replace the pump and turn it back on. Be sure to note the start and stop times and document the worker's activities. If you are doing multiple samples on various tasks, note the start-stop times and field notes for each sample. When you are done sampling for the entire day, turn the pump off, note the time of day, and remove it from the worker. Calibrate the pump again after sampling with the sample collection device connected to the pump. Again, SKC recommends that you use a sample collection device designated for calibration, but some prefer to use the actual sample from the field. The most important thing is to ensure that the post-sample flow rate is within 5% of the pre-sample flow rate. Otherwise, the sample is invalid and should be repeated. Take the average of the pre and post flow rates in liters per minute. Multiply by the total sample time in minutes to calculate the air volume in liters for each sample and supply the air volume for each of your samples when you send them to the lab. Got it? Particularly in the construction industry, sample duration is a big consideration because the individual tasks don't normally last the entire shift. In short, full shift sampling is the best option and is the easiest approach. But if you want to do short-term sampling, one of the most important considerations is how long do you have to sample to collect enough dust on the filter for the lab to actually measure it. OSHA suggests that a minimum sample time of 4 hours is required when using a sampler at 2 liters per minute in work environments near the silica action level. Major IH labs have advised SKC that they can do better than the OSHA minimum and can detect silica with minimum sample times of 2 hours using a sampler at 2 liters per minute at concentrations near the action level. So discuss this with the lab that you are using. Also keep in mind that the PPI is available in flows of 4 or 8 liters per minute if you wish to sample a shorter duration. Now that you understand the equipment, it's time to talk about how you determine compliance within the standard. It is critical for you to understand the 8-hour time-weighted average and how it is calculated. The 8-hour TWA is at the heart of the data interpretation in comparison to the PEL. The easiest option for calculating the 8-hour TWA is simply to collect one full shift sample. So when you get the results back from the lab, the silica concentration reported is the 8-hour TWA. No calculations necessary, one lab analysis less expensive. Particularly in the construction industry, some people want to collect multiple air samples throughout the day to document silica levels of various worker tasks. Keep in mind that monitoring a worker's task will help you choose the correct PPE or to evaluate controls, but the PEL is set as an 8-hour average. So, if you collect multiple samples throughout the day, you will need to do a calculation to determine the TWA. So let's now review how to calculate a time-weighted average. For purposes of comparison, let's start with the basics. In everyday life, we calculate the average of numbers by adding up all the numbers, then dividing by how many numbers there are. But in air sampling, we calculate an average differently. In air sampling, we calculate the average of the exposure level by taking into account time, the duration of each sample. Shown then on this slide is a basic formula for calculating the TWA for multiple samples. Concentration multiplied by time of sample 1 is added to that of sample 2, 3, or more. And the result is always divided by 8 since the PEL is an 8-hour limit. Okay, so that's not so difficult. But a frequent question from those new to air sampling is this: how do you compare the sampling results to the PEL when you don't sample the entire day? In this scenario, the safety and health professional must exercise some professional judgment. In short, why didn't you sample the full 8-hour shift? Was the concentration 0 for the rest of the day? Did the worker go on to another task without silica? Or was the concentration expected to be the same concentration for the rest of the day? That's not typical in construction, but it can be true in general industry. If the silica levels were expected to be 0 for the rest of the workday, then use the standard TWA calculation to determine the 8-hour time-weighted average as shown on this slide. Silica found in the lab multiplied by the time of sample, added to 0 micrograms multiplied by the time left in the day, all divided by 8. If the silica levels were expected to be the same, then just use the data from the lab as your 8-hour average. Either way, be prepared to defend your decision. In closing, let's talk about the real-time detection of silica. There are no inexpensive black boxes that data log and provide a direct readout in the field on levels of silica. There are, however, direct reading instruments that can detect, data log, and display levels of dust in general. These direct reading dust monitors do have usefulness in the field for things like perimeter sampling of regulated areas, quick and easy screening of worker tasks, help in choosing PPE and evaluating controls in the field, documenting transient changes in levels with work activities, detecting peak exposures, and recording history of exposures for record keeping. Shown on this slide is a direct reading dust monitor from SKC that is optimized for the measurement of silica. The SM4000 is designed as a supplement to compliance sampling. The SM4000 can be used for personal sampling by clipping the instrument to the belt and placing the sensor in the breathing zone. Alternatively, the device can be placed on a small stand for monitoring regulated areas. The SM4000 can see low levels of dust down to 1 microgram per cubic meter. The SM4000 also displays and data logs dust levels. It has an internal pump that allows users to also collect a filter sample for analysis, and it allows the addition of a respirable dust sampler for true respirable dust measurements. Thank you for your interest in silica sampling. Email any technical questions to skctech@skcinc.com and contact your local SKC rep for equipment and support.